I remember things. Hey, so welcome to our last class before break. Woo. Yeah, it do be that way sometimes. Do you guys still say that it do be that way sometimes? Is that still in the pop culture? That's passed out of the common vernacular? There are 5 things on the board. Several of them are super fast. We may have time to, I don't want to actually end class early. What I want to say is I will dismiss those people who are mentally checked out, mentally, spiritually, and emotionally checked out, and then I will continue to do anything that anybody votes for that would be helpful for y'all to understand, to improve. But yeah, I honestly don't think the vast majority of this is going to take the full period. We do have midterm coming up. So the last thing here is people often ask for a study guide. And I'm gonna present, here's what I would suggest you focus on. This is the majority of the test. Oh, by the way, just brief breaking things down. At least 20% of the midterm, I have decided, is simply can you identify equations in a proper context? If you just have alphabet soup on your equation sheet in your memory, if you just have symbols memorized without meaning, you will fail this 20%. You cannot get above a C. If you understand not just not just what the letters are, but what they mean and in what context they're used. When do I use capacitor versus when do I use point charge? That's an easy free 2-letter grades for you. Okay. As I have been saying, and like a broken record, time and time again, context, baby, and learn the foundations and look for the patterns. There we go. You could make a Tucker bot that just repeats that all semester. Ugh, that would be terrifying. All right, but the first thing is something particularly for the students, what MCAT and DAT doesn't have physics on, and I don't think OAT does electricity. So here's something just for the MCAT students. Chillax the rest of you. I'm going to introduce you to a brand new law of physics called Coulomb's law, and it is on the exam. What? Yeah, you need to know this too. Okay, just kidding. It's not a new equation, it's the old equation. I just forgot to name it. I was going to name it Bob, but instead I'm going to name it Coulomb. This is Coulomb's law. Yeah. This is on your exam. It's an old equation. You've seen this before. We introduced this a while ago. This is the point charge force formula. You should have seen this. Yeah, it's in your notes already. Better darn well be. The force that one point charge exerts on the other is K, 9 billion, times the product of the charges, the field and the dealer, divided by the distance between them squared. Yeah? All you need to know is, like, I'm not going to test you on what is the name of this equation. That's silly. But if MCAT talks about Coulomb's law, this is what they're referring to. It's nothing new. You've done this. You've seen this. Great. Check. We have done one of the points here. Yay. Point dose. What the what? What the what? What the? Oh, for God's sake, whatever. SI prefixes. This is still not perfect for a fair number of people. And I want to hit this because this is so easy. It's embarrassing to lose points on it. It can click. There's no, I shouldn't say that. That'll just make you feel dumb. Let me put it this way. This is an inch deep. There's no conceptual depth to this. There's a smidgen of memorization and then one skill that there's no sophistication here. That said, if you don't learn this, that's on you. Let me state what the prefixes are. I will not tell you this. I will not give these as hints. I want you to either know these or, for goodness sake, write them down on an equation sheet and be able to refer to them. I should also write the word. Kilo. If you see a kilometer, that is 1,000 meters, aka 10 to the third meters, one with 3 zeros after it. Mega is not going to appear on this test. Giga is not going to appear on this test. There are lots of others that exist, but I'm just going to list the things that I reserve the right to include in my problems for this test. 10 to the 0 is not called anything. 10 to the minus 2 is called centa. This one should be pretty darn straightforward and easy to remember. If you know that there are 100 cents in a dollar, that a cent is 1/100th of a dollar, 1 cent is 10 to the minus 2 of whatever you're talking about. That hopefully should be straightforward to memorize. Do you guys know how big a millimeter is, like on the ruler? Have you seen a ruler and looked at the metric size where there are little ticks inside the centimeters? Centimeters this big, right? Centimeters your finger, right? The little ticks, those are millimeter ticks. Now, to figure out the power for milli, just ask yourself, is there 1 tick in the centimeter scale? Are there 10 ticks? Are there 100 ticks fitting between each centimeter? No, it's 10 ticks between each centimeter. So if there are 10 ticks in between 1/100th of an inch, meter, that would mean there's 1,000 ticks in between, the ends of a meter stick. My point is, 1 milli is 10 to the minus 3, 1/1000th. Other than centa, everything we do, by the way, is powers of 1,000. 1,000, a thousandth, a blah, 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 blah. A millionth, a billionth, and so on. What? Why is that? Stop. Please note also, this is a little m. Oh, it's just a little m. If you put big M, that's mega. Case matters here. 1 micro. That's the Greek letter mu. 1 nano. Why is my freaking frackin' pen going weird? And the last one that I would teach you, that I would put on a test, last one that pops up frequently in electronics is pico. Pico, pico. Pico chew. No. Hey. Here's how I know these. I just remember the order. Milli, micro, nano, pico. And then I know that each in that order is 1,000th of what came before. If I know that milli is 1,000th, then everything else I can work out which is which. You don't have to memorize micro, -6, micro, -6, micro, -6, pico, -12, and pico, -12. If you just learn the order and the fact that they're 1,000, that they're a factor of 1,000 apart, this should not be hard. Okay, so maybe the memorization isn't the issue. Maybe the issue is then how do you apply that? Let's do an example. I'm going to teach you the way I was taught in 10th grade. It's a cute little box example. Let's find what 1 picocoulomb is equal to. We're not going to convert into number of electrons today, yet, right now. I just want to say, what is 1 picocoulomb in terms of, screw 1, heck with 1, 8 picocoulombs. I'm going to convert this into scientific notation, into the base unit of coulombs. Here's what you got to do. Here's all you got to do. I'm going to make a little box. You could do this for any unit conversions. And then I'm going to write, well, if the pico is on top, then I want to cancel it out, just like an algebraic variable. I'm going to put pico on bottom and coulombs on top. Now, the only thing to this is you've got to remember that 1 coulomb is 10 to the 12 picocoulombs, or 10 to the 12 picocoulomb, 10 to the minus 12 pico, or 10 to the minus 12 coulombs is 1 pico. You got to get it straight in your head. Here's how I think of this and check myself to make sure I don't get it backwards. Okay, a coulomb is a lot, a pico is a little. If I multiply by a big number or divide by a fraction, then I'm going to get a bunch of little, I'm sorry, a bunch of big things. If I've only got picocoulombs worth, I shouldn't get a bigger number. I shouldn't multiply by 10 to the 12. I don't ever memorize, let's see, picocoulombs is 10 to the minus 12 coulombs. I say, should there be a billion on top or a billion on bottom? And what makes sense to me is, if this is a tiny number of coulombs, I need to get a 10 to the minus something when I do it out. So I'm going to put 10 to the minus 12 here per 1 picocoulomb there. And I mean, you can also, if you prefer memorization, you could just say 1 pico unit equals 10 to the minus 12 units. So 1 pico unit is 10 to the minus 12 units there, if you prefer that way. I hate that though, personally. Your mileage may vary, void where prohibited, use whatever. Okay, and then at the end of the day, I just multiply across. It's a fraction. Pico over pico dies. 8 times 10 to the minus 12 goes by the name of, well, 8 times 10 to the minus 12. The unit that survives is the coulomb. You could do any unit conversion this way. Anytime you know that this measurement, this way of specifying something, 1 inch equals 2.54 centimeters, you could form a fraction with inches on top and centimeters on bottom, 1 inch on top to 2.54 centimeters on bottom, and there's the conversion factor to get centimeters into inches. If you know that 1 light year is, oh crap, I don't remember that. 4.28 parsec, light years is 1 parsec. You can multiply parsecs by light years per parsec to convert. You guys don't know or care what parsecs or light years are probably, unless you do an astro class. My point is you can do this with anything. If you know that this quantity is equal to this quantity, this conversion factor, then make a little box, cancel out, arrange it so that you cancel out the one you don't want, and you're done. Remember also the coulomb, the meter, the second, the newton, the joule, the farad. Our base units, except for kilograms, are just the unit itself. Kilograms are special in physics. We always use the kilogram as our unit of mass. Other than that, I suggest that you start a problem. You see a numerical problem, start by converting it into the base units. You see 8 picocoulombs. Great, that's a nice number. I'm going to convert it into some number of base units, coulombs. See what I'm stepping in? Smell what I'm stepping in? See where I'm going? There, that's my sermon about SI prefixes. Next, understanding capacitor energy. Sahu pointed out that this is a biggie that, oh, was it a week ago? A week ago was whoosh for a whole butt ton of people. Part of the problem here is that I've been dinking around with electronics for 30 years now, so I've in part forgotten what it's like not to know these as friends and neighbors. I would love it if you all could help me uh, 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 by asking questions about what does a capacitor do, or what's a capacitor look like, or whatever you feel confused about with capacitors, ask me and I shall help make more sense of it. But the first thing here is the energy formula. Remember 1/2 QV? Here is another way. I talked you through the idea of, well, the total charge, the total voltage is double counting. Maybe you don't like that. Let's make a graph of voltage versus charge. Charge, Q. Oh my God. If I make a graph of voltage versus charge on a capacitor, and I know that voltage is a constant times charge, what's this graph look like? Shoop. Or shoop, in this case. Yep, starts at 0, rises linearly. What's the product of two quantities look like on a graph? If I multiply two quantities, an x and a y, to get a total amount of something, what's that look like? It's not the slope. Slope is a ratio. The product of charge and voltage, the total accumulated amount of charge times voltage. If I have a final amount, if I've got up to, I've stored a Q final amount, and I observe that the final voltage is V final, which is, Q final over C. I can take the total amount of multiplied up QV as the area under the graph. If you've taken calculus, this is the integral. Who's at least taken calculus once in their life? Okay, you guys remember that you can multiply variables or functions by integrating the area under the graph? Great. So if you believe me that the total amount of QV, you don't need to remember calculus for this, just the idea. If the total amount of Q times V is the area under the curve, what's the formula for QV, total QV? What's the, oh, for God's sake, area of a triangle, 1/2 base times height. Bam! That's the formula I gave you. The total QV product, the total energy stored in the capacitor is just the integral, the area, the triangle, 1/2 base times height. Okie dokie pokey pony? What my father would say. Okay, this is the energy stored in a capacitor. No, really. Ask me a question. I always get better questions. Please turn to your neighbor, tell them what did Tucker just say and what's it mean, and then I want a question or two. Your turn. Turn to each other. Please. Okay, talk to me. Energy in a capacitor. Talk to me. What do you hear? Yeah, that's where that 1/2 comes from. By the way, the whole story that I told you, the idea that I told you is also contained in this graph. If you know that the area, the bits of area, the little rectangles of area represent how much energy it takes to charge the capacitor here versus how much additional energy does it take to charge the capacitor there versus how much energy does it take to charge the capacitor then. That story is here. The story I told you, remember I said the first bit of charge costs no energy to go on. Look, the area under that beginning tip of the triangle, the initial charge, has no voltage on the capacitor, so its QV is 0. As the voltage increases, the charge that flows on, the height of the rectangles of area that make up that area, the voltage that those little bits of charge experience increases. Each electron that flows onto the plates of the capacitor, each charge that flows onto the plates of the capacitor feels more and more pressure opposing it. The more electrons on, the more the pressure. Then they flow more on, so the pressure goes even higher. The pressure times the charge that is flowing is the energy to get that charge on. Since voltage keeps going up higher and higher, energy cost gets higher and higher. The total energy cost is not just final voltage times final charge, but it's an accumulated from zero, from an initial zero, to a final value, 1/2 base times height. You believe me more now about that half? Okay. Okay. I'm going to do a problem in a minute. Revisit and talk about an electron is launched from the negative plate of a capacitor and smacks into the positive plate of a capacitor. We derived a formula for that before, but that was still wrecking some people on Discord, so I wanted to touch on that guy again. But before we talk about capacitors, we've got a formula for energy. Before we talk about a specific problem with capacitors, I'm begging you, help me remember what's hard about capacitors in general. What doesn't click for you? And as specifically as you can, Mitzi, awesome. Ask me.
Battery have current flow through it, and then the negative or the electrons will accumulate at the capacitor, but they won't go to the next plate, they just accumulate. Is it? Flow through it if electrons are just being stored again.
How can electrons accumulate on the negative plate and positive charges accumulate on the positive plate if the electrons can't hop the gap? I don't actually need to talk about the resistor at all. If the electrons can't hop the gap. Okay, let's think about the instant we connect a battery to a capacitor. What happens to the electricity? The whole point of a battery is to suck charges up from its negative side, pressurize them, give them a voltage, and spit them out the positive side. When I connect an uncharged capacitor, charge is pulled off of the negative plate of the capacitor. Positives leave behind negatives. That's actually a lie, but you can ignore the fact that that's a lie. We can pretend, and it doesn't make one bit of difference to anything we do except for one specific topic I'll talk about after break. Doesn't make any difference that it's actually minuses that move. Imagine little pluses moving. Little pluses are slurped by the battery. They're attracted to the negative terminal of the battery, and the battery gives it energy to pump it uphill, up voltage. When I suck positives away from the negative plate, what's left behind? Negatives. So the negative terminal of the battery causes, for God's sake, why you do that, Apple Pencil? Causes negative charges to be left behind. What's its positive terminal doing? You suck, you blow. Charges, that is. Okay, so this is pushing those positive charges that it has taken off the negative plate of the capacitor, pushing them out. Where do those land? Does anyone know why Apple Pencils and an iPad might possibly start to do that? See if it's like a Nintendo. Oh, you guys know that reference. Ah, finding the old people in the audience. So again, Mitzi's question was, how do the positives and the negatives, how do the negatives get there? Or how do the positives get to the other plate if they can't hop the gap? And my answer is, any given electron doesn't need to hop the gap. It'll be siphoned off by the whatever the positive side of the power supply is. There could be other circuitry in here, but still, if current is flowing like this through across the plates of the capacitor, you're going to be siphoning charge off this side and shoving charge onto that side. Give you a better picture of what's going on, Mitzi? Yeah? Do you want to ask a follow-up, please?
Um,
What do you mean voltage goes? Voltage doesn't go, current goes. No, no, no.
well, that is-
You're crazy. Space is crazy. Are you asking how there can be a current like that around, or are you asking how there can be a voltage across the capacitor after this charging happens? Okay, how can there be a voltage? I was offended by the term voltage going. There will be a voltage across the capacitor. There is a voltage anytime plus and minuses are pulled apart. The voltage reflects, or, you know, pulled apart or hoovered around a circuit to be opposed, to be in different places. Remember what voltage is. Voltage tells us how much energy each of those charges, each coulomb worth of those charges, how much energy that has. If the charges are separated, plus and minus are attracted. They want to come together. The energy of being separated, or for that matter, these pluses are pushing each other apart. They want to escape each other. The energy stored in the electrostatic attraction and repulsion of charges that are pulled apart, that's the origin of why there's energy stored in the capacitor, why there's a voltage across a capacitor. Anytime you have separated charges, anytime you have compressed like charges, that's an energy. That's a voltage. Let me make sure I get this right. So, um, the attraction will store energy. If my mind, I believe that this is beyond the scope of the class, but the fact that the plus charges are near the other plus charges, they are much closer than the pluses are from the other minuses. So I believe that the amount of energy stored in plus being near plus and minus being near minus, that's way stronger than the attraction inside. So I believe that the answer to your question, not that it's actually going to be tested on at this level, is that that is by far, by orders of magnitude, the bigger force, the bigger energy. Just like, half a second, just like in an air tank, the air doesn't want to be next to it itself. There's that pressure there. The pressure of a capacitor is the like charges repelling each other.
uh, Proportion stronger than the attraction.
The plates are attracted to each other, but you hold them in place. You put something between them so that they can't glomp together. They can't recombine. Not across this gap anyway. And yes, if my memory of calculus-based hardcore physics major is correct, the energy stored inside each plate of the capacitor by having like charges is the major factor. I'm not sure of that, but I'm pretty sure. Good questions, good questions. Other questions to get a feeling for capacitors and capacitance. Okay, let me do one more problem. Sorry, one more problem. Let me do a homework problem for you relating to that, relating to that what? Relating to that example we gave before. Charge inside. Oh, that's just terrible. Life is such suffering. Here, we're going to use the capacitor. I mean, hell, our first look at capacitors and capacitance, I don't care that they're bleedingly useful, common foundational electronic components. This entire time we've been talking about capacitors, we've been focusing on how field is related to voltage, the energy inside a capacitor, blah, 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 that sort of thing. We haven't needed to talk about other crap. Here's about the practical application. Here's the fundamental. We're going to deal with this not as an electronic component, but something that makes a constant voltage difference from side to side, something that makes a steady electric field inside. If I've got a random electron freed from the, crap, what's that called? Chemical potential? No, crap. Oh, I forget. Freed from the negative plate, allowed to zip across a vacuum gap between the plates, then free space between the plates, I can find out how fast it's going, how much faster it gets perhaps, by using the law of conservation of energy. Law of conservation of energy states that total energy does not change when there are no external other forces. The electrical energy and the kinetic energy are the only two things going on. I mean, theoretically, there's gravitational energy, but the weight of an electron is so ignorable you can't even imagine. So what I could say is, let's release this sucker from rest and see how fast it gets. Well, I think the energy of a point charge at voltage V is QV. The energy that the energy, for God's sake, the energy that the point charge has is QV. I'm not talking about the total energy that the capacitor has, right? So I don't use 1/2 Q total V total. I'm using one whole charge of the electron, voltage of the capacitor. This turns into 1/2 M V final squared. Now, I give you a homework problem where I ask you, if I add charge to the capacitor, calculate how that affects the final velocity. I want you to be able to reason, not just with numbers. I don't give you all the numbers in this. I want you to reason with the structure of the formula. Let me reason as follows. How does charge on the capacitor affect the voltage of the capacitor? If charge doubles, what happens to voltage? It doubles. This is direct proportionality. Q is a constant number times V. Does it make sense that if you multiply the left side by 2, the right side has to be 2 times as big, right? Okay. So whenever you have Q equals something times or divided by, this could be a fraction, but it is got V multiplying that fraction or constant. This is constant proportionality. This is called proportionality, direct proportionality. This side doubles, this side doubles. This side triples, this quantity triples. This side divides by 10, voltage will divide by 10. Assuming you're keeping capacitance constant, which we are. So if I say I double the charge on the capacitor plates, the voltage doubles. Well, in this equation, if I know the voltage doubles and I'm asked about the final velocity, reason for me, reason how velocity is affected by voltage. I think it might be helpful to solve for velocity. Constant multiples, screw them. They don't matter. I'm going to solve for velocity, and I'm just going to drop I'm just going to drop the constants, the multiples. Those don't matter. They don't do anything. The ratios cancel. How do I get rid of a square root? How do I get rid of a square? I take the square root, yeah? So this says that V final varies not as the directly proportional, but proportional to the root of the voltage. I have deduced if Q doubles, V doubles. If V doubles, what happens to velocity? Velocity increases not by a factor of 2, but by a factor of square root 2. So my chain of reasoning is to find a series of equations that link the quantity you are told about to the quantity that you want to know about, and then reason, how does this affect that? How does that affect this? Or perhaps that affect this is the easier way to see it. You can also, if I recall correctly, I did this briefly in week 3 of this semester. You can also bullshit numbers and plug them in. What I said a moment ago about constant multiples, they don't do anything. They don't matter. You can plug in any number for constants that don't change, and the reasoning does not shift. Does the capacitance change? No. So I'm just going to pick a random number for C. I pick 1. So then Q equals 1 times V, for God's sake, equals 1 times V. That looks like IV. I'm just going to write V. And this equation, the charge of the electron, 1.6 10 to the negative 19, screw it. It's a constant. I can just pick 1. Equals 1/2. I'm going to round half to 1. Mass of the electron, 9 times 10 to the minus 31, I'm going to round to 1. Our chain of equations has turned into charge equals voltage, voltage equals square root velocity. Therefore, by the principle of substitution, charge equals square root of velocity, okay? So just by bullshitting all the constants and making them something that makes the equation stupidly simple, I get that charge is the square root of velocity. Then what you could do is you can plug in the multiplier. The problem I gave you says what happens if charge doubles. If I plug in double the charge as like 2 units of charge instead of 1 unit of charge, solve for V final. That tells you not the value of V final, but the ratio of new to old. Again, just like I reasoned through a second ago for you, I get square root 2 when I solve for V final. The velocity is root 2, 1.4-ish, times as great as it was. I give you an initial velocity, multiply by square root 2, you're done. Final velocity. Okay, this is so much easier than calculatoring out every last individual intermediate value. I'm going to give you problems on the test where I wouldn't even give you the capacitance of the capacitor. You can't actually do this purely by calculate next value, calculate next value, calculate next value. Sometimes I'll give you enough, but it's faster and easier if you develop the, the, the ability to reason from the structure of the formulas. How does this affect that? How does that affect the other? How does the other affect the last? Do you feel okay with this strategy? I want you to turn to your neighbor and I showed you 2 ways to do it. Pick one and tell them how to do this sort of problem. Then I'll take a question. And I'm going to put a practical example up for when you're done. Questions on what you just told each other? All right, here's an exam problem. Maybe, potentially. This is totally something I could give you. By what factor, what is the ratio of forces of the new force to the old force? How does the force between 2 point charges change when I triple the distance between those charges? You have to know the formula that relates these quantities. What is the formula for force between 2 point charges? I just gave it to you. Hmm? Hmm? This is Coulomb's law. Okay, now, second method I just showed you, this factor, this ratio method works with any values for the not changing constants. K, constant in nature, never changes. Q, I'm not talking about how does the charge affect the force. So I'm just going to round all these values or pick them as one. I'm going to say force. I'm going to evolve this equation to force equals 1 over r squared. If you actually want to calculate the force in newtons, this is wrongo bazongo, but it doesn't matter when we're reasoning about factors. Now I say, what did I do to distance? It becomes 3 times as great as it was. I'm just going to say it starts at 1 and it ends at 3. So the force was 1, and now it's 1 over 3 squared. The force is not 1/9 of a newton. The force is 1/9 as big as it was before. So you could say in a sentence, when the distance between 2 point charges triples, the force changes by a factor of 1/9. The force becomes 1/9 as great. Force loses 89% of its strength. Questions? Does this feel okay? Frankly, I think that you're never going to use the formulas we do again in the rest of your life. I, getting my PhD, never used more than a handful of things that I had spent 5.5 years of physics undergraduate learning. The point is not the individual equations. I strongly believe that the point is, for this class, why your majors make you take physics is to sharpen your intelligence, make you learn something hard so that you learn how to learn better, and teach you some math. Here's a skill, reasoning, not using your calculator, but using logic, that I feel can actually change the way you see the world. When you hear about increases or decreases, the federal budget went up by 5%. Holy crap balls, that's a lot of money. Or NASA's budget went up by 5%. No, NASA's budget is really quite small comparatively. So if I'm reasoning about the ratio, the relative size of things, or for that matter, to say that if you know that your tax is 20% of your income, don't even remember if that's right. If your tax is 20%, that's directly proportional. Tax equals 0.2 times income. You can reason about how, oh, if I make twice as much money, how is my tax bill going to change? It's roughly going to be twice as great. Now, that's a rough estimate. Taxes are not actually linear, and there's something called the standard deduction. But you can get a rough order of magnitude estimate for a lot of things if you know that this is a constant fraction of that. Regardless of the thing, in the real world, you can figure stuff out. Okay, okay, okay. That is those are the homework problems and specific skills that I think are absolutely necessary that you should not leave this week without knowing. If you are drained and ready for break already, get out of here quietly. I'm going to start the study guide. No, you're not going? A couple of you are going. Okay, go, go, go. It's okay. You can go. I'm going to start the study guide for everybody who's mentally still not dead. Here are the foundational equations. I'm always talking about know the foundational equations. I'm going to break this down into dose facts and trace tables for you. I hear that people like tables or graphics or whatever. I drew this up really nicely. Forced off. What I claim, these are absolutely going to be tested upon. I told you this multiple times. These are the defining equations, the foundational relationships which are always true. Here's your first graphic. FU, everybody. Just kidding. Force, energy, potential, energy, electric field, voltage. You have to know what the letters mean. I mean, always. I'm going to show you the equations that let you get from one to the next. The relationship between force and potential energy. How does potential energy change? The change in potential energy is equal to negative the work done, negative the force times the distance. Electric field is defined, always true, defining equation here by the idea that if I take force and divide it by the charge feeling it, I'll get a test charge independent measure of how strong this electrical stuff is. Electric field is a measure of the sources alone, not specific, the force of the sources, not specific to the amount of test charge you got. Voltage, same thing with potential energy. Frankly, this is all I would memorize for you for the defining equations. And then, if I ask you about electric field versus voltage, well, hold on. Force divided by charge, energy divided by charge. If I just divide the first equation by charge, what do I get? If I divide the first equation by charge, I get an equation linking E and V. Energy per charge is? Force per charge is? How do I find how much voltage changes in an electric field? Negative, multiply the electric field times the distance moved along it. You see how that is the previous equation? Okay, So that is your first quadrant. Oh, well, what if I tell you force and ask for voltage? If I tell you force, first you could find field, and then you could use field to find voltage, or how voltage changes anyway. Yeah? So you could connect these. Hell, if you forget change in energy is negative force times displacement, you could even work backwards, find electric field, find the change in voltage, use the change in voltage to find the potential energy. You can work backwards if you forget something. So these are the defining equations, the always true equations, the equations that I'm guaranteeing I'll ask about at least one. Point charges. I can ask you about FU, EV. And here, these aren't linking one term to the next. They're just equations for each term. You can actually get energy from force if you know calculus. If you can integrate, 1 over r squared becomes 1 over r. But this isn't a calc-based course. You don't need to be able to do that. For your perspective, you can just memorize. I don't suggest you memorize E and V. I suggest if you know the foundation, you deduce E and V. Here's force. What happens if I divide out little q? The resulting formula just doesn't have a little q. What about voltage? Divide out little q. Look, if I know the principle, I've cut in half the number of things I have to memorize. I must know context. If I'm talking about point charges, bam. If I'm talking about a relationship, a fundamental, always true thing, I have to use these relationships. So context, context, context. You can't speak a language if you don't know what you're talking about. Inside a capacitor, FU, EV. Hey, Merry Christmas. We're not going to talk about the force between plates of a capacitor. Just going to tell you, we haven't talked about it. We're not going to talk about it. We could talk about the force on a charge inside the capacitor. Oh my God, I said capacitor. No, you don't need this. If I talk about the force on a charge inside a capacitor, I have to have given you the electric field. That's a fundamental equation thing. Context, baby, context. If you know what the terms mean, you can recognize just because the word capacitor appears, I will have given you enough to find a reasonable way. Do not panic if you see something. If you see force and capacitor in the same sentence. Okay. Electric field inside a capacitor, our starting point. Whoopsie. Oopsie. I can't write. Oh my God, I can't think either. Q over A epsilon. This is where we started. Now, the glorious thing about capacitors is their field is uniform. So we don't need to integrate. We don't need calculus to find out the total amount of electric field equals volts per meter. The voltage per meter, for God's sake. The voltage is the electric field times the, just like we had before. Oh my sweet, yes, right, yes, okay, I thought I wrote it wrong. Just like I had before, if I want voltage, I could just multiply electric field times the distance that that field is pointing. What is the distance between plates of the capacitor? I usually call it D. Bam! Bam! I didn't need to memorize it. If I know what the letters mean and the context, there's a formula you can get not from memorizing, but just stuff clicking. All right, and if you've got energy, we can go back to the foundation and say QV is the foundational, but as we've spent a fair bit of time doing, you get the total that way. That's how I encourage you to write it anyway. You could shove the lower V in, that would still be a true statement above, but you do gots to know that there is that factor of half that will kill you if you ignore it. Okay, that's like no, there's one more. There's one more for capacitors. And C equals Q over V. Then if I can rearrange, if I ask you about capacitance and electric field, or capacitance and energy, or voltage and capacitance, you have to be able to plug in symbol for symbol and resolve. For instance, if I plug in V here, an always true statement about capacitors, into the definition, the always true definition of capacitors, then I would get Q over Q cancels, D over A epsilon naught downstairs, flippy flippy, A epsilon naught over D. Oh my God, that's the separate formula that we got, but you don't need that. You can deduce it. It can come from other crap. Now, you don't want to deduce stuff. You're scared on the test, you're racing, you just want to have something on your equation sheet. Okay, sure, that's fine. You can write an equation sheet with all the pink formulas on. But if you recognize the patterns, you're going to catch mistakes much more easily. If you know that QD over A epsilon is related to Q over A epsilon naught, is related to capacitors, you're not going to mistakenly plug this in when talking about point charges. There's my sermon. That's 90% of what you need. The 100th percent, the only other equation that I can think of is the idea that there are 6.25 times 10 to the 18, I'll just say protons, in 1 coulomb. So if I wish to convert between number of coulombs and number of fundamental particles that coulomb is, I can multiply coulombs times constant equals protons, or electrons if it's negative. And that's just a conversion factor. If I recall correctly, pretty sure I do, I've given you every equation that you need to solve every darn problem on the test. Everything on the test is either one of these or a combination of two of these, smushulating them in together. If you can reason about these, if you know these, if these are friends and neighbors to you, then everything gets easier. I'm not saying that it's necessarily easy. You still do have to be able to reason and interpret the questions as given. I'm not saying there's nothing to it, but there are a lot of people walking around without knowing their core, and if you don't know the words of a language, you can't learn to speak it intelligently. Learn the foundations. Know these. Think about them, and especially their connections, and it's not as bad as it looks. Okay, I'll probably say this twice more before the midterm, because it's good advice, and I love you. But there's my sermon. There's your study guide. Know these equations, understand them, look for the connections. That's half of your exam. Question. The point behind those examples is to get inside what voltage inside a capacitor is, and that you don't always use the half QV. That specific example, including half MV squared, is not on the test. I'm not going to have you say initial equals final energy. I mean, we haven't done kinetic energy in a minute. Theoretically, I shouldn't include something from a previous semester. Oh, Ricardo asked, include the values. What I'm going to say is if I forget to give you a foundational thing, epsilon naught, K, whatever, then you can ask me and I'll put it on the board. I'm going to try, do my darndest to include those constants. I will not tell you the SI prefixes, the multipliers. I want you to know those. But everything else, all the fundamental constants I'll give. Selena? That particular equation is not needed for this test. Unless I am greatly mistaken, that doesn't appear on the practice test either. I have cut that, I will cut that off of this exam. No, 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 no. No, no, no. This is 100% of the exam. Either uses these or reasoning about qualitatively, not plugging in, but reasoning about them. At least 20% of the exam will be literally just state. If I say capacitor electric field, can you give me the formula? Do you know what the letters mean? Can you plug? Can you state the equation? Um, I split the remainder roughly evenly between concept and plugging in numbers and solving for crab. Yeah. But all of these are all you need. If you know them, if you understand them. I think I was going to bump it up to 25 because, you miss a couple of questions and then you're screwed. I'm going to bump it up to 25. Always the scantrons you must provide, or I'll give you a stern look. Make you beg your classmates. Very. Yes. I am embarrassed that I don't remember if I cut out the velocity kinetic energy equation from last year. It's last year's midterm is the practice for this year. If that does appear, I will go in and fix it, but you may have already downloaded it. If you haven't downloaded, if that does appear, those specific questions aren't there. The idea about energy in a capacitor and QV being okay to use for point charges inside, that is on. Yeah.
This one gonna have like multiple questions, or it'll be like last one, but like no like multiple answers.
No, I'll just put two questions that ask the two parts that I want. I'm Nope, that's not true. That's not true. But I'll tell you exactly what I would ask. What changes the capacitance of a capacitor? And it's not charge and voltage. Merry Christmas. Do you guys all know that? Charge and voltage don't control capacitance. There we go. That's the only thing that I would ask you, and I'll tell you exactly that.
Remember when we did polarization, induction, and conduction?
Uh-huh.
Different steps in order to do that.
That's to get a feeling about the electricity. I don't know great questions to ask about that. I think all that is included in here. I'm not going to ask about induction polarization. No, just because I can't think of good questions about them. Anything else? I hope you all have the best break of your lives, but don't break yourselves, okay? And I hope my freaking kids get healthy at the same time. Ugh.